Morning. Now for something completely different. Well, not exactly completely different, because you heard from Jane earlier on this morning with two applications of Drillhole Spacing Analysis, DHSA. Here's the third one. And in this case, what we're doing is something a little bit more maybe complex. And we're looking at generating pseudo drill holes from simulated data and comparing it with estimated models. So we'll go through this. So essentially the task in this particular case was what is the optimum spacing for drill hole grade control holes. So what we're going to go through, talk a little bit about DHSA drill hole spacing. James already touched on this to a certain extent. We'll go through this paradigm of value optimization and misclassification, which I think you'll probably be familiar with. Talk a little bit about the methodology, which is co-simulation, and then we'll go through a case study. It's a real case study. I've just made it anonymous. So drill hole spacing, why is it important? For grade control in particular, what we want to do, obviously, it's a very expensive activity. We don't want to spend more money than we need to. And if we want to achieve a certain level of classification, indicated or measured, let's say, we want to optimize that. So essentially, we want to maximize the drilling and minimize the cost. So we want to achieve that cost-benefit trade-off. So this slide, a little bit complicated, but I think you've probably seen all this before. So what we're looking at here is we've got this quadrant, which is looking at estimated grades on the y-axis, on the x-axis, sorry, true grades on the y-axis. And we're applying a cutoff grade, and that divides our situation into four segments. The first segment, the one we're interested in, is where we predict the material to be above cutoff grade, and in reality it is above cutoff grade. So that's material that is ore and we're mining it as ore. The second one is material that's below the cutoff grade estimated, and in truth it is below the cutoff grade. So that's waste that goes to waste. The two we're not interested in, or rather the two we're interested in minimizing, is this one, number three here, sorry, number three, which is where we predict the material to be above the cutoff grade, and in fact is below the cutoff grade. So this is effectively dilution. And the fourth quadrant, number one, is where we predict material to be below the cutoff grade, and in reality it's above the cutoff grade. So that's all loss. So you can see that we've got costs associated with that. The green quadrant, number two, that's revenue, that's fine. Number four is waste, and we've simply just got the mining cost of that. Quadrant number one is material that we're losing the value of, and quadrant number three is additional waste material that we don't really want to mine, but we are. So you can see there we've got estimated grades and we've got true grades. Well, where do we get the true grades? Well, the answer to that is we get the true grades from the simulation of grades, and we'll go through that. The estimated grades we generate from an ordinary Krieg block model. So just in terms of cost, there's many ways that you can do this. This slide's a bit complicated, but let's just focus on the key points. Quadrant two, we've got the revenue. That's the value of the material that we're mining that minus the cost of mining, minus the cost of processing. Quadrant four, we've got the mining cost, no revenue. Quadrant one, we've got the value of the material that we're sending to the waste dump. Quadrant three, we've got the cost of processing and mining material that's got no value in it. It may have some value, but for the purposes of this, we assume that it's got no value. And then, of course, what we're trying to optimize here is the drilling costs, and as you know, the more holes you drill, the more it's going to cost you. So we're looking to optimize the value of the drilling, and we're looking to compare the revenue. Now, there's quite a few assumptions and simplifications. For this exercise, the one that we made was that every block had to be mined. Therefore, we didn't necessarily need to consider the mining cost. It was constant, assuming that every block needed to be mined. And the other assumption was that the quadrant three material here is below the cutoff grade, as I mentioned to you, no revenue. So in other words, just a mining cost. Now you can complicate this by assuming that you would have an opportunity cost. In other words, if you're displacing higher grade material from the plant by feeding it waste, you're actually losing money by not putting the high grade material through that. It gets complicated, but really that's something that you can take it a little bit further. The key point is this idea of the balance between the mine and the mill, whether your mine is feeding the mill, whether you've got more material or less material than the mill can take. So that's the theory. Simulation, I probably shouldn't go into simulation. Simulation's a way of generating dense grids of data, and some of the features of the simulation that we're interested in is that if it's done correctly, we're honouring the histogram of the input data, we're honouring the variogram of the input data. To a certain extent, it minimises conditional bias, doesn't eliminate it, but importantly, simulation or realizations produce a number of outcomes which are equally likely, and it allows us to choose one of those outcomes which honours the input data. And this is the key application here. We're looking at choosing a simulated realization that honours the drill hole data for reasons that should be obvious, will become obvious. So that's simulation. In this case, we actually use multivariate simulation, which is in Supervisor, and the key point of multivariate simulation, as I'm sure you realise, is to reproduce in the simulated model the variability in the input data. So if we consider an example where we have iron, silica, manganese, alumina and phosphorus, some variables have a positive correlation, silica and alumina, some variables have a negative correlation, iron and silica, and some variables have little or no correlation. And what we're trying to do with multivariate simulation is to preserve that correlation or the lack of correlation in the data itself, in the simulation, in the set of realizations. And the key point here is that, as I mentioned to you, once we've got a simulated grid of data that honours our drill holes, we can then sample that to get various drill spacing. That really is the key activity here. What we're doing is we're generating multiple pseudo drilling grids, and then we can compare those drilling grids back to the original model, and we can look at using that misclassification paradigm. We can look at the value of that, and at the end of the day, we can select the value that gives us the best value for money. So that's the framework. Let's go through a case study. This is a real case study, nickel copper mine, or nickel copper ore body, I should say. It's not a mine yet, it will be. To start off with, we had to do a little bit of manipulation of the data. So the ore body is folded in two senses. So what we did using a Datamine macro, we basically created a false Z coordinate, and we flattened the ore body out. So essentially we had a flat block model which defined the zone for the simulation, and the drill holes are flattened as well as the model. We generated multivariate simulations. Given the time, I don't really have time to go into this. This is one of the two multivariate simulation methods available in Supervisor. It's an additive log normal ratio transformation. Essentially, what we're doing is we're taking multiple variables and we're transforming them into two independent variables. Those two independent variables are then converted to normal scores, and we're using a quite simple sequential Gaussian simulation. So the trick, if you like, or the smart bit is this ALR transformation. So we're doing this with our nickel and copper, which are correlated in this case. Here's some pictures. Here's the raw data in flattened space. Here are the histograms of the nickel and the copper, and here's the scatter plot of the raw data within that ore body. So there's a moderate correlation between nickel and copper. Here's the Gaussianisation. So what the software has done, it's created these two independent variables. Now you could obviously use this with five variables. In this case, there's only two. And what we've created is F1 and F2. Those two variables are independent, and they've been turned into normal scores. And this plot here shows that there's no relationship effectively between the F1 and the F2. What I should say to you, this is not the nickel and the copper. These are the independent variables. They don't correspond to the particular elements. Here's the after the simulation. Here is a scatter plot of the simulated data. Again, we can see that to a certain extent, and it's distorted a little bit by the scale here, but it's essentially uncorrelated. And then what we can do is we can back transform the data, and we have then a set of simulated values that more or less preserve the correlation between the original input data. Just to prove that, here's the data from the original data. This is nickel and copper, and here is one of the realizations. You can see that they're pretty well spot on. So what we've done now is we've generated, in fact, we generated 10 realizations, and we chose one. And that one best represented the statistics of the input data. So now what we've got is a dense grid of data. In this case, it's a 10 by 10 by 10 model, and then we can use that to represent our truth. So now the way to go now is we're basically generating a whole series of pseudo drill hole grids from our single simulation that reflects the input data. We can use that data to generate a series of ordinary Krieg models for nickel and copper at the SMU scale. In this case, the SMU scale being 10 by 10 by 5. Our drill holes are various spacings, but in each case we're using a dice 5, which is an offset pattern. So we're looking at 10 by 10 spacing, 15 by 15, 20 by 20, and 25 by 25. Obviously, you can do as many as you want. We're generating the models, as I say, we're comparing those back to the original simulation, which is the truth. We're doing our value accumulation, and we're calculating the net cost of misclassification, also considering the drill spacing, the drill cost, I should say. Here's the original selected simulation. Now, clearly, there's a few artifacts there of the process. You know, it's not perfect, but those artifacts don't affect the outcome. As I've shown you, the simulated values do reflect the histogram and indeed the variogram of the input data. This is copper, this is nickel. And this is a set of drill holes that was extracted from that data. We just used Datamine macros to do this. And this is 10 by 10 drill holes. So look, obviously it's quite dense. This is quite a big area. And in close-up, this is what we've got. This is just the drill holes on this dice 5 pattern, 10 by 10. So 10 by 10 drilling, 15 by 15, 20 by 20, and 25 by 25. So each of these is effectively a set of pseudo simulated drill hole data, which we can then use to generate ordinary Krieg models, which we can then use to compare back to the original truth or simulation. So we need to calculate the value, and in this case, because we're dealing with a multi-element ore body, nickel and copper, we did it in terms of the NSR. And what do we need to do that? Well, obviously we need the nickel and copper prices, foreign exchange rates, the recovery as a function of the grade. We need payability, transport, treatment and refining charges. Obviously we need to know how much it's going to cost to drill the holes and assay them, processing cost, and then obviously a cutoff grade. So all of the stuff you would normally have when you were doing a grade estimate, which we got from the client. So you can do some interesting things, and here's one of the things you can do. You can generate a misclassification map. So what we're looking at here, this is one of the simulations colored on nickel grades, and now what we're looking at here is it's colored on the misclassified blocks. So in other words, where we've got ore that is mined as ore, it's blue. Where we've got, anyway, the colors don't exactly match, but you can see that there's 4 colors there, and those 4 colors correspond to the quadrants in there. So we can, even without looking at any values, we can define the areas of misclassification. In this case, as you might imagine, the areas of misclassification tend to be the lower grade areas around the high grade material here. So that's an interesting plot, but it's not getting us to our objective, which is to define the optimal drilling grid. Here's a comparison of the copper and nickel. This is for one of the models, 10 by 10 model. So what we're doing here is we're generating a 10 by 10 grade control model based on that pseudo drill hole data, and we're comparing it against the simulated values. So this is a hex bin plot, just a scatter plot basically. And of course, what we can do is the cutoff here, 0.15%. We can compare the estimated data against the true data. So we've got these 4 quadrants. So we've got the 3, which of course is our dilution, quadrant 1, which is our ore loss, quadrant 4, which is our waste, quadrant 2, which is most of the information. So as we go from a fairly tight drill spacing to a fairly wide drill spacing, you can see how those quadrants vary. So clearly you can assign a net value to each of these quadrants here, and you can calculate that for the 10 by 10 model, and you can also calculate it for the 15 by 15, the 20 by 20, and in this case the 25 by 25. And as you would imagine, by the time you get to a wide drill spacing, you've got a lot more misclassification. So here's the results. This graph simply looks at the drilling cost relative to the most dense grid, which is the 10 by 10 grid. So we're looking at the 10 by 10 grid at 100%, 15 by 15, 20 by 20, and 25 by 25. Clearly, there's a big difference or big decrease in the number of holes between there and there and there and there. So the relative cost impact is quite significant. You can see that the 15 by 15 cost is only 48% of the cost of the 10 by 10. After that, it gets a little bit less variable. So going from 10 by 10 drilling to 15 by 15 drilling, we have a huge drop in cost. The question is that drop in cost offset by the increase in revenue or net revenue that we get? So here's some other information. We can also look at the percentage of the total tons that are misclassified. So remember, we're looking at these 2 quadrants here, ore loss and dilution. Here's the various drilling grids, and here's the proportion of the total tonnage, not metal, but the total tonnage that is misclassified. So you can see when we have a 10 by 10, ore loss quadrant is quite small. Dilution quadrant is a bit larger. As we increase the spacing, you can see that it increases, but maybe not as much as you would imagine. In this case, as you can see, and as you can see from there as well, the dilution quadrant is a lot more significant than the ore loss quadrant. Going backwards. So the relative contributions of the dilution and the ore loss is a function of the cutoff grades. It's also a function of the relative grade of the ore body and the relative difference between the high grades and the low grades. So if you've got a transition from high grade to low grade, you're going to find that your ore loss and dilution quadrants are going to be quite different. If you have some high grade areas and some low grade areas, then it'll be different. And what I would say is that this formulation, in other words, the value, the net value, it's a relatively simple formulation. You could make this a lot more sophisticated, as I mentioned to you, by considering misclassification cost, opportunity cost as well. So here's some results. And again, remember what we're doing here is we're comparing estimated grades for an ordinary Krieg model with the truth being the simulated grades. And along this axis here, we're looking at the 10 by 10 drilling grid, the 15 by 15, the 20 by 20, and the 25 by 25. And our net revenue formula is very simple. It's simply the revenue that we get from the ore minus the value of the material that we send to the waste dump, minus the cost of the dilution, and then of course we're considering the drilling cost. And in this case, you can see that here's the results. More drilling does not necessarily generate more revenue. In this case, our 10 by 10 drilling, which is a huge drilling cost, doesn't give us the maximum net revenue, I should say. And in fact, we get that at the 15 by 15 drilling case. So in this case, you could see that if we wanted to maximize the value of our grade control spacing, we can generate that on the basis of 15 by 15 drilling. So it's a bit complicated, a bit of work involved, but it's a whole series of fairly simple steps. As I said to you, this bit here can be made more complicated, but in this case, it was a fairly straightforward approach. So we have two metals in this case, but you could do it for multiple metals because the simulation technique handles many variables. The net revenue formulation, it's simplistic but realistic. Remember, I mentioned that we could make it more complicated by considering the opportunity cost. The key point, as I did mention to you, is this mine-mill production balance. So it's if depending on the balance, in other words, the rate of the material produced from the mine versus the capacity of the mill, the cost might change. The key step is getting a realistic simulation of the data. And once you've got that, you can generate your pseudo grids and off you go. That's it. Thank you. David.
You had a graph, I think it was of the drilling costs against the, it was on a percentage axis.
Yeah.
10 by 10, you had 100%?
Yeah, that's right. It's drilling cost relative to the 10 by 10 grid.
I don't understand how the relative thing is working, because you've got 15 by 15 like minus 50 or something. So
what I'm saying, if it costs $10 million to drill the ore body out, 10 by 10, it would cost $4.8 million to drill it out on 15 by 15, 4.2 million and 4 million, something like that. So it's the total cost of the drilling out the entire ore body at that spacing relative to the cost of the 10 by 10.
Does that mean the first one should be at 0?
Well, 100%. I mean, you could do it in the other way if you like, but this is the total cost. This is the proportion of that total cost at wider drill spacings. Does that not make sense?
I'll leave it.
Ross.
Looks like your grade control model is very accurate and cost effective. So I just wanted to ask, if we were to look at a scenario where using a form of policy solution, we lowered that mill factor, but the measures throughout the line is preserved, do you think that would change the optimum cost of the grid spacing because of how you actually can use more accurate grade control model because of how it's transposed?
Well, we don't actually have a grade control model. Well, that's the whole point. We're generating a pseudo grade control model from the drilling. So we don't. None of this mine hasn't started yet. So nothing's actually happened.
I guess what I'm trying to say is that the optimality of the cost is directly proportional to how well they can recover that, right? So if the recovery improves, does that warrant the type of...
True. Yeah, as I mentioned, there's lots of modifications you could make. You could look at recovery as a function of grade and so on. So yeah, there's many ways you can make this more sophisticated. If you like, this is just a starting point, but illustrates the technique. Glavy.
Hi. I was just wondering, you choose one simulation to generate all the graphs and then revenue. You know they are all equiprobable, but some of them will be a lower grade simulation than a high grade. If you pick out other simulations, do you actually have the same results?
You would have different results, yeah.
But like, you still choose that 15 by 15?
I don't know, but the underlying principle is that you choose the simulation that reflects the input data, the truth. So if you chose one that was less reflective, then you might get a different answer.
So when you say less reflective, you're looking at, so they all produce the diagrams, so you're looking at the one that produces the best solution.
Yeah, as you know, there is variability in realizations, and some of them reflect the variogram and histogram less well. So we chose the one that reflected the variogram the most accurately. And in fact, statistics reflected the input data. If you use variability, then you're introducing another element of variability in there, which of course you could do, for sure.
Well, my question was more to what Flavio just said, that you just chose one realization, which is, and the other realization are probable.
That's right. When we say equiprobable, anyone that does simulation knows that there is variability, and that variability is a function of the variogram and the data. In this case, it's base metal data. There was quite a small amount of variability between the realizations, but they're not entirely equiprobable. Thank you.